evening, everyone, and welcome to this Sunday evening update on this Sunday, January 24th, 2010, the first show of the new year. And, of course, this is the place where you get all your news and views of life extension from around the world, broadcasting from the office, the head office of the Immortality Institute here in Wausau, Wisconsin. I'm your host, Justin Lowe, and, of course, the show helping us along, of course, is Ustream, the magic of Ustream, which allows you to see this live streamed program all over the world and interact with the text chat. Do not forget about that. As we get into our special guest for tonight in the interview, you can ask questions, and tonight's guest, of course, as you perhaps had heard earlier, is Peter Passaro, Research Fellow at the University of Sussex in the UK, and the topic is neuroscience, brain-computer interfacing, and longevity. Of course, Peter, many of you remember, is a longtime member and participant at the Immortality Institute. Just a reminder, again, as I just mentioned, you can ask questions in the text chat as we roll along. I hope everyone enjoys the new codec that we've had installed here for the program. The video feed, a little bit better, although, maybe you don't want to see my bald head and all that higher resolution. I don't know. What matters is the audio, and we did have a little technical trouble earlier with our special guest, but should be ready and waiting in just a second. And remember, after the interview is over, we have a little bit more news and some other highlights, things that have been going on around the Institute in the world of life extension over the last couple of months. It's been a while since we had a show. A lot of new things coming up, especially the director elections at the Institute. The board of director elections going on right now. I'll have more details on that coming up in just a bit. I am going to bring up a little picture here of our guest for tonight before our official introduction. And, of course, it's Peter Passaro, and at this point, I am going to give him a nice warm welcome, and really a nice time to speak again with Peter after so many years. He's been so busy. Welcome to the program tonight, Peter.
Hi.
Hello, and as I just mentioned, it's been so many years since I've had an opportunity to speak with you. How about a little introduction for the audience members out there tonight, and a little background on what you've been up to researching over the last few years for your dissertation? Just a brief summary, I guess.
Okay. So I'm currently a research fellow, which is a postdoc position at the University of Sussex, getting ready to finally take my doctoral viva examination, so I'm not quite a doctor yet.
Okay.
Hopefully very, very soon. So as anybody who had seen the previous chat knows, I was at Georgia Tech working with Steve Potter, and it was there that I was trained to use multi-electrode arrays. And at that time I was working in cultured systems with multi-electrode arrays, rat or mouse cortical cultures grown in a single layer of cells onto these multi-electrode arrays. Since I moved to the University of Sussex, I've started working in what we call a whole brain semi-intact system. So what I've been doing is essentially taking the entire brain out of a snail now and putting that onto a multi-electrode array, and working on developing that system for recording. And for the past couple years, my focus has been building a software system for rapid extraction of information about the system. So finding cells, finding their locations, estimating how large they are, and then estimating the connectivity. So the end result of this is to quickly come up with maps of just by putting the tissue down on the multi-electrode array, to find all the cells and find the dynamic connectivity between them.
All right.
So that's the short version.
Okay, that's the short version. That's all we need tonight. And I was going to ask now. I'm fairly new. I'm a neophyte when it comes to this type of research issue with brain-computer interfacing and the colloquial brain in a vat. How big is a snail brain? Like, what are the physical dimensions on that?
It's about 1.5 millimeters to 2 millimeters in diameter, 20,000 cells in total.
Only
in comparison to, yep,
20,000 cells. Wow.
So it's one of the simplest brains you can really still call a true brain in the animal kingdom.
Okay, and what I was reading with in the abstract of your recent paper was that you're using that to monitor the feeding mechanisms in the brain of the snail. Is that it?
Yeah. So that's the idea would be eventually to expand to the whole brain. In fact, it was funny. I was looking back at the transcript of that talk I gave a long time ago.
A long time ago, yeah.
Yeah, and there was a question in there about, is there any organism in which we completely understand it, we can completely model the brain? And the answer is still no. To this day, there still isn't. So one of the motivating factors for doing this, for me, is that this with only 20,000 cells, with the recording hardware that's coming online now, and with the development of better software techniques, we might actually, and within my working lifetime, certainly, I would think, be able to get at the large-scale dynamics. But, okay, now back to the feeding system.
Yes. Okay.
So we selected the feeding system because it's the most well-known. There's been a lot of intracellular recording with glass electrodes, but you can only do a few of those at a time in this system. So there's a lot known about the feeding system already. So we've used that backbone to start building on top of with the multi-electrode array technology now.
Okay. And you mentioned that there's the recording hardware and the software, very important part about this as well. And you are involved in that as well, right? Developing some new software that will speed along the analysis of these large brain structures?
Yeah, so after I did the initial development on the system, I handed off the recording to the first author on that paper, that's Chris Harris.
Okay.
And I've spent the last 2 years doing software development. So really that's our big bottleneck. We can record a tremendous amount of data, but figuring out what all that data means is still a huge challenge. So I'm trying to speed that process up as much as I can.
Oh, okay. So that's the proverbial next step then in getting more of the whole brain emulation toward the goal of whole brain emulation. That's the next step, is figuring out a way to handle all of this data that's coming out of a brain, even a very small one like the snail brain.
Yeah, absolutely. So so we're currently recording with 60 electrodes. We just pulled in another grant, so we'll be moving up to a 256 electrode system now. So I'm about to get a lot more data than I was getting before.
I guess so. Now, you start out with 60 electrodes, and that enabled you to monitor the activity in one small region of the snail brain. Now, it's the 250 electrode system. How much greater of a percentage of the brain will you be able to monitor then with that larger array?
Well, it depends on what we want to do. So it would make my job easier on the analysis side if we use the same size array with just a higher density. But it also we could use an array with a much lower density, where the electrodes are more spread out. We could monitor more of the brain. Yeah. So it's all a trade-off on what you want to do. But there are commercially available arrays at different scales, and you can order one to scale within a certain range as well.
Okay, so if you went with a higher density, you could monitor more neurons within the gastronomical part of the snail brain, but you could also spread it out to more of the brain and not get as much impulse data, basically.
Yeah.
From the brain. I see. And you mentioned 20,000 neurons in the snail brain, and you're already up to 250 electrode array. It doesn't sound like it would take that long to get most of the brain under